Electron affinity. What is electron affinity, and why does it generally become less negative moving down the periodic table? In this video, we'll be talking about Coulomb's law, shielding, and the periodic trends of electron affinity. Consider an electron and a neutral atom. When the electron is added to the neutral atom, there is going to be energy released. Electron affinity is a measure of this energy. It is the energy released when a neutral atom receives an electron, making a negative ion. Electron affinity sounds very similar to the concept of
ionization energy. By definition, ionization energy is the amount of energy needed to remove the outermost electron in an atom.
Electron affinity, on the other hand, is the measure of the change in energy associated with the formation of the bond between two atoms. Although they are similar concepts, they are different. However, they are still related. This equation demonstrates this concept. Because an electron is added, the atom becomes negative. A general rule of thumb is that electron affinity is negative because energy is released. More negative means more energy is released. Now let's take a look at some periodic trends. To start things off, we'll talk about alkaline metals. They have a hard time gaining electrons. They prefer to lose electrons to form cations. This is because their valence electron shell is relatively empty, so it's easier for them to lose an electron than to gain a bunch of electrons. Because of this, electron affinity is low in metals. On the other hand, nonmetals like to gain electrons. This is due to them having more electrons, thus making it easier to form a stable octet. One exception to this is the noble gases. They already have a full octet, so gaining an electron will put it in a new energy level, which is unstable. Noble gases have low electron affinity. As you can see, electron affinity decreases from left to right in the chariot. However, energy is released, so although the number is decreasing, the energy release is increasing. You can also see that electron affinity decreases going down the family. I will explain this later. Let's discuss some exceptions to these rules. Beryllium and magnesium have unusual electron affinities according to this chart. This is because their electron configuration ends in the s subshell. Adding one electron resides in the p subshell, which is considered unstable. Group 15 elements are also strange. They have a half-filled p subshell, so adding another one would make things unstable. Halogens are one electron away from a stable octet, so they have high electron affinities. Attraction is really important for electron affinity. As the electrons increase in number, the atomic radius decreases in distance. Looking at Coulomb's law, F equals kq1q2 over r squared, attraction is inversely proportional to the radius squared. As such, the smaller the radius, the greater the attraction. This brings us back to the question of why electron affinity decreases down the family. As more electrons are added, the attraction should increase, right? This is not the case, however. But why? The answer is shielding. But what is shielding? Suppose we have an arrangement of electrons, like so. If we were to add one electron to it, like so, then electrons would start repelling each other because they're all negative. These electrons would also repel, as well as these ones, as well as these ones. Basically, repulsion between electrons increase down the periodic table, creating more distance. Coulomb's law says that more distance means less attraction, and less attraction is less electron affinity. Electron affinity, to summarize, increases from left to right because the addition of new electrons increases the force of attraction. It also decreases moving down because the shielding effect increases the distance from the nucleus to the valence electrons.